All right, strap yourselves in because today we are going deep into antimatter.
Antimatter, huh?
Yeah, one of the most mind-bending mysteries in physics.
Absolutely.
So we're going to tackle the big questions.
Lay 'em on me.
What is antimatter? Where does it come from?
Okay.
Why does it seem to have vanished?
Yeah, that's a good one.
And what are scientists doing to unlock its secrets?
You know, it's interesting because you always hear about antimatter.
Right.
Like it's straight out of Star Trek.
Yeah. Oh.
But it's a fundamental part of our universe.
Exactly. So we're going to separate the science fiction from the science fact.
That's what we're here for.
We're going to really unpack this whole thing.
I like it.
And you know the thing that always gets me
What's that?
is this whole idea that the Big Bang should have created equal amounts of matter and antimatter.
Right, that's the theory.
But our universe is overwhelmingly made of matter.
So where did all the antimatter go?
Exactly. It's like the ultimate cosmic whodunit.
I like that.
But before we get too deep into that,
Okay.
let's make sure we're all on the same page.
Good idea.
What exactly is antimatter?
Yeah. Good question.
It's not just matter with a bad attitude.
Uh-huh. No. It's way more interesting than that.
I figured.
Think of it like this.
Okay.
Every particle of matter
Mm-hmm.
has an evil twin,
Okay.
an antiparticle.
Okay.
And they have the same mass,
Mm-hmm.
but opposite charge
Okay.
and quantum numbers.
Quantum numbers, we don't have to get into that right now, do we?
No, not for this.
Okay.
But so, for example, an electron,
Okay.
which has a negative charge,
Right.
has a positively charged antiparticle called a positron.
A positron. So they're like mirror images of each other,
Exactly.
but with a crucial difference in the charge.
Yep.
I got it.
So what happens when these matter and antimatter twins meet?
Well, do they just awkwardly avoid eye contact at the cosmic coffee shop?
Haha. No.
Okay.
It's much more dramatic than that.
All right.
When matter and antimatter collide, they annihilate each other,
Finale.
completely destroy each other.
Oh, wow.
In a burst of pure energy.
Wow.
It's like they completely cancel each other out,
Okay.
converting their entire mass into energy, according to EMC.
Einstein's famous equation.
Exactly.
So it's not just a science fiction concept.
Nope.
Annihilation is a real thing.
Very real.
And this happens all the time.
Well, not all the time.
Okay.
Antimatter is actually extremely rare in our universe.
Right, right.
But we do see evidence of annihilation
Got it.
in high-energy events.
Okay.
Like when cosmic rays slam into Earth's atmosphere.
Oh, okay. So these cosmic rays
Yeah.
are kind of like little messengers
In a sense, yes.
from the antimatter realm.
They give us clues about the processes
Okay.
that create antimatter naturally.
Naturally.
And they also remind us that even a seemingly ordinary object, like a banana.
Hold on. A banana.
Yes, a banana.
What does a banana have to do with antimatter?
Well, it emits a positron roughly every 75 minutes
What?
because of the decay of potassium-40.
My breakfast is spitting out antimatter.
It's a very small
That's
nut.
both terrifying and awesome.
It is pretty cool.
But, okay.
Yeah.
If antimatter is so powerful, and it was supposedly created in equal amounts to matter during the Big Bang,
Right.
why isn't our universe just a constant fireworks show of annihilation?
That, my friend, is the million-dollar question.
Yeah.
Or perhaps the trillion-dollar question.
Okay.
Given the theoretical cost of producing antimatter,
Right.
it's a problem known as the matter-antimatter asymmetry.
The matter-antimatter asymmetry.
Yeah.
So it's not just that we haven't found big chunks of antimatter out there. The real mystery is why there's so much more matter
Right.
than antimatter in the first place.
Exactly. If the laws of physics were perfectly symmetrical,
Okay.
the Big Bang should have produced a universe with equal amounts of matter and antimatter.
Leading to total annihilation.
Exactly. We wouldn't be here.
But we are here.
But we are.
So there's a fundamental imbalance somewhere.
There is.
Some tiny difference between matter and antimatter
Yeah.
that allowed matter to win out in the early universe.
That's what we think.
That's wild.
Scientists believe this imbalance, however small, must exist.
Okay.
And they're looking for it.
So they're digging deep
Very deep.
into the laws of physics to find this tiny crack in the symmetry.
It's like searching for a needle in a cosmic haystack.
It's pretty amazing, isn't it?
It really is.
And speaking of incredible feats,
Yeah.
scientists at CERN
Of course.
have managed to create and trap anti-hydrogen atoms.
Wow. Not just antiparticles,
That's
but
right.
actual atoms.
Anti-hydrogen atoms?
The antimatter counterpart of hydrogen.
That's incredible. So what can they learn from studying those?
Well, by comparing the properties of antihydrogen
Okay.
with regular hydrogen,
Yeah.
They can search for any tiny deviations.
Okay.
That might explain the matter-antimatter asymmetry.
So it's like holding a mirror up to the universe.
Exactly.
And looking for these subtle imperfections in the reflection.
That's a great way to put it.
It's amazing to think that something so seemingly small,
I know, right?
like a tiny asymmetry in the laws of physics,
Right.
could have such profound consequences for the existence of our entire universe.
It highlights the interconnectedness of everything.
Yeah.
It really drives home the point that even the tiniest details can have a massive impact on the grand scheme of things.
So these experiments at CERN are like looking for a cosmic fingerprint,
Yeah.
a clue that could help us solve this whole mystery of the missing antimatter.
Exactly.
What else are scientists doing to track down this elusive stuff?
They're looking in some pretty unexpected places.
Oh, yeah. Like where?
Like Earth's Van Allen belts
Yeah.
and even the magnetospheres of gas giants.
Really? Why there?
Well, there's a theory
Okay.
that these regions might trap antimatter particles
Okay.
from cosmic rays. And if we could somehow collect them,
Collect them?
we might have a more readily available source of antimatter.
Hold on. Are you suggesting we could mine antimatter from space?
Some researchers believe it might be feasible.
Wow.
Of course, there are immense technological challenges.
Right, I imagine.
You'd need a way to safely capture and contain antimatter
Yeah.
in the harsh environment of space.
It's not exactly a friendly environment.
And then you have to transport it back to Earth
Right.
without triggering a catastrophic annihilation event.
I can see why they haven't sent Bruce Willis up there yet,
Huh.
but it's still an incredible concept.
It is very futuristic.
Imagine harvesting antimatter from the cosmos.
It would be a game changer for sure.
But even if we could collect it,
Mm.
what would we do with it?
Well, that's where things get really interesting.
Okay.
Antimatter have the potential to revolutionize everything,
Everything.
from medicine to space travel.
All right, so let's dig into that before we explore those possibilities.
Yeah.
Let's delve a little deeper into the fundamental research.
Lead the way.
All right, let's take a closer look at what scientists are learning about antimatter's properties and its role in the universe.
All right, sounds good. One of the most fascinating areas of research is the study of CP violation.
CP violation?
Yeah.
That seems kind of cryptic.
It is a little bit.
Can you break it down for me?
Sure.
Like, what's so important about it?
Well, it gets into the symmetries of the universe.
Okay.
CP stands for charge conjugation and parity.
Okay.
Charge conjugation
Yeah.
is essentially flipping the charge of a particle.
Okay, like we talked about with antiparticles.
Exactly.
Okay.
Parity
Yeah.
is like looking at the mirror image of a physical process.
Okay.
So if the mirror image behaves the same way, parity is conserved.
Okay.
But sometimes it's violated,
Violated.
meaning the mirror image acts differently.
Okay, so CP violation means both charge and parity are flipped, and the behavior changes.
Exactly.
What does that have to do with the missing antimatter mystery?
Well, CP violation
Yeah.
is a key piece of the puzzle.
Okay.
If the laws of physics were perfectly symmetrical
Uh-huh.
with respect to CP,
Mm-hmm.
matter and antimatter
Yeah.
would have been created and destroyed in equal amounts,
Okay.
leaving nothing behind.
So basically we wouldn't exist.
Okay.
So the CP violation,
Yeah.
it's like a tiny imperfection
Yeah, you could say that.
in the mirror,
Mhm.
a subtle asymmetry that allowed matter to win out over antimatter.
Exactly.
Wow, so have we actually observed this?
We have.
CP violation?
We've actually observed CP violation in certain particle interactions.
So that means that the universe doesn't always play by the same rules
Nope.
for matter and antimatter.
It seems to have a slight preference for matter.
That's pretty mind-blowing.
But it is.
So how do scientists study something as subtle as the CP violation?
It requires incredibly precise measurements
Yeah,
and very carefully designed experiments.
that makes sense.
And one of the key facilities for this kind of research is CERN.
CERN. Okay.
It's always at the forefront.
They're doing some pretty groundbreaking work over there.
They are, yeah.
So what are they doing at CERN to investigate this?
Well, they have an experiment called LHCb,
LHCb.
and they're studying the decays of particles
Okay.
called B mesons.
D-mesons. Okay.
These particles are fascinating
Okay.
because they contain a bottom quark,
Okay.
which is a heavier cousin of the up and down quarks that make up protons and neutrons.
Okay, so the way these B-mesons decay can reveal subtle differences between matter and antimatter.
Exactly.
So by studying studying the debris from these particle decays,
Yeah,
they can look for clues about CP violations.
exactly.
It sounds like a very indirect way to study something.
Yeah, it is.
That's so fundamental.
But it's incredibly powerful.
Okay.
By analyzing vast amounts of data from these decays, they can tease out tiny deviations
Got it.
that would be impossible to detect otherwise.
It's like looking for a faint whisper amidst a cacophony of sound.
That's a great analogy.
So we've got scientists meticulously studying these particle decays at CERN,
Yeah.
hoping to find that whisper of
Yeah.
CP violation.
That could explain this whole asymmetry thing.
But let's step back for a moment
Okay.
and consider the bigger picture.
Good idea.
Where does antimatter fit into our understanding of the universe?
That's a great question.
Like, could there be entire regions of the universe made of antimatter?
It's a possibility.
Antimatter stars and galaxies.
Mind-blowing to think about.
Would they look any different from regular galaxies?
That's the challenge.
Yeah.
It would be very difficult to tell them apart
Why is that?
because they would emit light and radiation.
Yeah.
Just like regular galaxies do.
So how could we tell them apart?
Well, the key would be to look for the signature of annihilation events.
Oh, so if an antimatter galaxy
Yeah.
collided with a matter galaxy,
Yeah.
it would create a huge explosion of energy.
It would be a cosmic fireworks show
Wow.
of unimaginable proportions.
And how would we see that?
It would release a tremendous burst of gamma rays.
Gamma rays.
Yep.
So are astronomers looking for these gamma ray bursts
They are.
as like potential signs of these antimatter galaxies
Yeah.
colliding?
Out there in the vastness of space.
Wow. And have they found anything?
Not yet,
Oh.
but it's one of the most exciting
Yeah.
and challenging quests
I
in
bet.
astronomy.
Because if we could find a region of space
Mm-hmm.
dominated by antimatter,
It would revolutionize our understanding of the universe.
it would certainly be a game changer.
Yeah.
So we've got these tantalizing possibilities of
Mhm.
antimatter galaxies out there
Yeah.
and the mind-boggling research at CERN.
Absolutely.
But what about here on Earth?
Oh, here.
Are there other ways that scientists are studying antimatter?
Of course.
Oh, yeah.
Scientists are also trying to measure
Okay.
the gravitational interaction of antimatter.
What does that mean?
Well, we assume antimatter falls down,
Okay, like gravity?
just like regular matter.
Right.
But there's no definitive experimental proof.
So you're telling me there's a chance that antimatter could fall up?
It's highly unlikely.
But that would rewrite the laws of physics.
It would be huge.
So they're actually going to test this?
Oh, yeah. Scientists are meticulous.
Okay.
They want to test every assumption.
Makes sense.
There are experiments underway,
Hmm.
like the LPHAG experiment at CERN,
Okay.
which aims to directly measure the gravitational behavior of antihydrogen.
So they're going to basically drop antimatter and see what happens.
Essentially, yes.
Wow.
They trap and cool antihydrogen atoms
Okay.
and then carefully observe their motion in a gravitational field.
That's incredible.
Is
What are some of the other groundbreaking areas of antimatter research?
Well, one area
Okay.
that has captured the imagination of scientists
Yeah.
and science fiction writers alike
Oh, yeah.
is the potential of antimatter as a fuel source.
Oh, like spaceships.
Exactly.
Antimatter-powered spaceships.
Imagine harnessing the power of annihilation
Okay.
to propel spaceships to distant stars.
That's where the science fiction aspect really kicks in.
It kind
How realistic is that? Like,
yeah,
are we anywhere close to that?
it's still a distant dream.
Okay.
The challenges are formidable.
Yeah.
First and foremost,
Yeah.
we need a way to produce and store significant amounts of antimatter.
And that's
Difficult and expensive.
like trillions of dollars expensive.
It's a hefty price tag for fuel.
And then how do you even store it?
Right, that's another huge hurdle.
Because it annihilates on contact.
Exactly. You'd need some kind of magnetic or electromagnetic trap
Oh.
to keep the antimatter isolated
Yeah.
from any matter.
And I imagine that even the slightest leak
Yeah.
could be catastrophic.
It'd be a bad day.
So antimatter-powered spaceships are probably not happening anytime soon.
Not anytime soon, though.
But it's still an incredible concept.
It is very intriguing.
It highlights the incredible potential of antimatter,
Absolutely.
even if it's still largely theoretical.
At this point, yeah.
But even if we never achieve interstellar travel with antimatter,
Mm-hmm.
the research that's being done
Mm-hmm.
to understand its properties and control its behavior
Yeah.
is already yielding benefits in other areas.
Like medicine and material science.
Oh, okay. Speaking of practical applications,
Yeah.
I know antimatter is already being used in medical imaging,
That's right.
specifically PE scans.
Yep.
But are there other potential uses being explored?
Well, one area that holds promise
Okay.
is cancer therapy.
Cancer therapy.
Yeah.
How would that work?
Scientists are investigating the use of antiprotons
Okay.
to target and destroy cancerous cells.
So, like, radiation?
The idea is to use the precise energy release of annihilation to deliver a lethal dose of radiation
To the cancer cells,
directly to tumors.
while minimizing damage to surrounding healthy tissue.
Exactly.
So it's like a super precise form of radiation therapy.
That's the goal.
Wow.
It's still in the experimental stages,
Okay.
but it shows the potential of antimatter
Yeah.
to make a real difference in people's lives.
That's incredible.
It is.
It's amazing to think that something as exotic as antimatter
I know, right?
could one day play a crucial role in healthcare.
It's pretty mind-blowing.
But before we get too ahead of ourselves,
Okay.
let's rewind for a moment.
Right?
We've been talking about all the amazing things antimatter can do,
Yeah.
but we still haven't fully addressed the fundamental mystery of why it's so rare.
Right. Good point.
What are some of the leading theories
Okay.
about the matter-antimatter asymmetry?
That's a question that continues to baffle scientists.
Yeah, but
There are many theories,
okay.
but one of the most compelling involves a phenomenon called leptogenesis.
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 Okay, how could that explain
Yeah.
the dominance of matter over antimatter?
Well, it involves the decay of heavy hypothetical particles
Yeah.
called leptoquarks
Leptoquarks.
in the very early universe.
Hold on, hypothetical particles.
Yeah.
So these are particles that we haven't actually observed,
We haven't observed them yet.
but they're predicted by some extensions of the standard model.
That's right.
Okay, so these leptoquarks, if they exist,
Okay.
could have decayed in a way that produced a slight excess of matter
Yeah.
over antimatter in the early universe.
Exactly.
And then that tiny imbalance
Yeah.
would have been amplified over time,
As the universe expanded and cooled.
leading to the matter-dominated universe we observe today.
That's the idea.
So it's all about these tiny asymmetries,
Right.
these subtle violations of symmetry.
That have shaped the very fabric of our universe.
That's wild. Is there any experimental evidence to support this?
Not yet. It's a very difficult theory to test
Okay.
because it involves processes that occurred
Yeah.
at incredibly high energies,
Higher than what we can create.
far beyond what we can achieve
Okay.
in our current particle accelerators.
So we need even bigger,
Yeah.
more powerful particle accelerators.
To recreate the conditions of the early universe.
And test these theories.
That's right.
And are there plans for that?
Oh, yeah.
Like in the works?
Those kinds of facilities are being planned and developed.
The future of antimatter research is pretty exciting.
It is. There's a lot to look forward to.
It sounds like we're on the verge of some major breakthroughs
I think so.
in our understanding of antimatter
Yeah,
and its role in the universe.
absolutely.
So what are some of the most exciting developments that you see on the horizon?
Yeah, it really feels like we are.
There's so much happening right now.
But, you know, before we get too carried away with all these theories and stuff,
Yeah,
let's talk about the practical applications of antimatter. All right, bring it back down to Earth.
exactly. So
Yeah.
what are some of the ways
Mm.
antimatter is being used right now?
Well, we talked about PT scans
Right.
and the potential for antimatter-powered spacecraft.
Yeah. And the cancer therapies.
Exactly.
Okay, let's start with PT scans.
Right.
I've always been kind of fuzzy on how those actually work.
I could explain that.
Yeah, please.
So PT scans rely on positrons.
Those are the antimatter twins of electrons.
You got it.
Okay.
So basically,
Yeah.
a small amount of radioactive tracer,
Okay.
which emits positrons,
Mm-hmm.
is injected into the body.
Okay.
And these positrons travel a short distance
Okay.
before encountering electrons in the body's tissues.
Okay, so they meet up,
They meet up and they annihilate each other,
releasing energy.
producing two gamma rays that travel in opposite directions.
Okay.
And the PET scanner detects these gamma rays.
Okay.
And a computer then uses that information to create images.
So it's like they're using the energy from matter-antimatter annihilation to create a map of the body.
Essentially, yes.
That's pretty cool.
And because these gamma rays can penetrate tissues,
Yeah.
PET scans can provide really detailed images
Okay.
of organs and tissues that are difficult to see with other techniques.
That makes sense.
So it's really powerful.
Yeah, it's incredible how something so abstract can have such a direct impact on healthcare.
I agree.
And, we talked about antimatter-powered spacecraft earlier.
We did.
I know we're not building warp drives anytime soon.
Not yet, at least.
But how realistic is the idea of using antimatter as fuel for space travel?
It's definitely a long-term goal.
Okay.
The challenges are significant, like we discussed.
The cost, the storage.
Exactly. But the potential benefits are so enticing.
I mean, the energy density is just mind-blowing.
It's insane. A tiny amount could theoretically power a spacecraft for years.
Years.
And because annihilation produces pure energy, you don't need those bulky fuel tanks.
Right.
Or complex engines.
An antimatter engine would be so efficient and lightweight.
It would be revolutionary.
Are there actual research efforts happening right now?
Yeah, there are.
Focused on developing these kinds of propulsion systems?
Absolutely. A number of research groups around the world are working on this.
Wow.
Some are focused on producing and storing antimatter more efficiently.
Okay.
Others are working on the magnetic confinement systems.
To keep it contained.
And some are even working on how to control the energy release.
To create thrust.
Exactly.
It sounds like even though we're not building antimatter spaceships just yet, there's a lot of groundwork being laid.
Oh, yeah, it's a long-term goal.
But the potential rewards are huge.
Imagine exploring the solar system and beyond.
Powered by the most efficient fuel imaginable.
It's a pretty captivating vision.
It is. And you also mentioned that antimatter could play a role in cancer treatment.
Right. So researchers are looking into using antiprotons as a form of radiation therapy.
How does that work?
So the idea is to exploit the fact that antiprotons release most of their energy when they annihilate with matter at the end of their path.
So you could basically target a tumor with a beam of antiprotons.
That's right.
And they would deliver a very focused dose of radiation.
Minimizing damage to the surrounding healthy tissue.
That's incredible. So it's like a super precise form of radiation.
Exactly.
And it could be much more effective than conventional methods.
That's the hope.
Wow, that's amazing.
It's still in the early stages of research, but the results are promising.
It's just remarkable to think that something as exotic as antimatter could have such a profound impact on healthcare.
And this is just the beginning.
Yeah.
As we continue to learn more, we're likely to discover even more ways to use it.
We've covered a lot today.
We have. It's been a great discussion.
So before we wrap up, what are some key takeaways you hope our listeners will remember?
Well, I think the main thing is that antimatter is not just science fiction.
It's a real phenomenon.
It's very real.
That's playing a huge role in our understanding of the universe.
Absolutely. And it's not just about these esoteric theories either.
Right. It has real-world applications.
It's already making a difference in our lives.
With medical imaging and cancer treatment, and who knows what else is in store.
The possibilities are endless.
I think it's safe to say that antimatter is one of the most mind-blowing and thought-provoking topics in all of science.
I agree. It really makes you think.
It's like a journey into the heart of the universe.
And a journey that's just beginning.
Well, on that note, I think it's time to wrap up our deep dive into antimatter.
It's been a pleasure.
It's been a fantastic discussion. Thank you for sharing your expertise with us.
Anytime.
It's been an incredible journey.
I encourage all our listeners to keep exploring the fascinating world of antimatter.
There's so much to learn.
Who knows what amazing secrets and possibilities await us.
And to our listeners out there, we'd love to hear your thoughts on this episode. Head over to our website or social media channels and let us know what you think.
And remember, the universe is full of wonders.
And the more we learn,
the more we realize how much there is still to discover.
So keep exploring, keep questioning.
And keep that sense of wonder alive.
That's a perfect note to end on.
It is.
Thanks for joining us for this deep dive into antimatter.
My pleasure.
Until next time, keep looking up and keep those minds curious.